This is going to be your video for lesson 33, applying quadratic functions, or applying quadratic equations, I should say. At this time, I'd like you to go ahead and pause the video and annotate your learning targets, as well as go ahead and do your spiral review questions. So number 1 and number 2, because those are our review. Okay, so number 1, it's asking us to determine if the data in the table represents a linear function or not, and then to explain. So looking at letter A, we have a possible answer here. Keep in mind that, you could have something that isn't worded exactly like mine, but still kind of says the same thing, so don't feel like you have to erase your answers. You could always just add to them or modify them as needed. This is a linear function because there is constant change in the x and the y. So this over here is plus 1, plus 1, plus 1. This over here is minus 4, minus 4, minus 4, minus 4. So you see that constant change in both the x's and the y's. Letter B, it is a linear function because when graphed, the ordered pairs are a straight line. So although you can't see the constant change in the table necessarily, you do see it when it's graphed. So that would definitely be a linear function because it creates a line. Letter C, this table right here, it is not a linear function because there is no constant change. Also went ahead and graphed it and it doesn't form a line, it forms a U-shape. So as soon as you hear that U-shape description, you should also be making the connection that that is a parabola or a quadratic function. And then finally, letter D, it is also not a linear function because there is no constant change in the x and y values. And when graphed, we notice that it formed a J-shape. So hopefully as soon as you're hearing that description of a J-shape, you're making that connection with an exponential function with that J-shaped graph. All right, number 2, revisiting the concepts of discrete and continuous. So a discrete graphs are unconnected points plotted on the graph. The variables typically represent something that fractions and decimals cannot be used, like books or tickets or people, things where you wouldn't have like a half of it or a fraction of it. Letter B, continuous graphs are connected points plotted on a graph. The variables typically represent something that fractions and decimals can be used, like time, height, temperature, etc. So, you could have 1.5 hours. You could have 3 3/4 feet, things like that. In other words, you would use a continuous graph when having data between the distinct points is appropriate. So think about, you would connect because all of the data points in between those whole numbers, so to speak, are reasonable. Okay, we are ready for task 2. I do want to point out a little typo here, if you could help me fix this. We are not ready to graph the equation yet. So let's cross that out for now. We'll get there, I believe, in number 4. When you're ready, go ahead and pause the video, read through task 2 introduction, and then I would like for you to go ahead and do 3, 4, and 5 on your own, and then we'll come back together to kind of compare answers. Okay, so you probably investigated the table of values a little bit and noticed that this is not linear because there's no constant change in both the x and the y variables. In order to be linear, there would have to be constant change in both. And of course, when you found the difference between your y values, your consecutive y values, you noticed that it was not a consistent difference or a consistent change. So definitely not linear. When you did number 4 and you graphed it, you got something like this. And so that probably gave you a better idea of the fact that, of course, it's not linear, but even helped you narrow it down even more into what type of nonlinear function this is. And hopefully you have an idea of that. Looking at number 5, should the data here be discrete or continuous? Well, we are dealing with height and time, so because both of those do allow for the fractions and decimals to be appropriate, the data here would be represented by a continuous graph. In order to reach these different heights, the rocket would have to, hit all of the points in between there. It's not just going to, teleport from height to height. It has to ascend or descend according to this model here. All right, we're ready for task 3. Looking at task 3, I would like for you to go ahead and try numbers 6 through 8 on your own, and then we'll bring it back together to compare answers. Okay, looking at task 3, number 6, how high was the rocket when the engine burned out? Use the table graph to support your answer. Well, of course, you want to see, basically how high did it go and, when did it start essentially falling and no longer ascending but start descending. So I said since the device will begin collecting data when the engine runs out, I know that the height at 0 seconds is the height when the engine burned out, 512 feet. All right, looking at number 7, how long did it take the rocket to reach its maximum height after the engine cut out? It took an additional 2 seconds for the rocket to reach its maximum height after the engine burned out. So the engine burned out, it continued because it was already being pushed with that kinetic energy. It continued to ascend for a brief period of time, about 2 seconds before it began to descend and free fall because the parachute did not open. And once the rocket begins to descend, it is in free fall. Estimate how long it was in free fall before it reached the ground. So of course down here would be when it reached the ground, and it was in free fall from about here to here. So depending on how you interpret the graph, it could be anywhere from 4 to 10 seconds reasonably. I would like for you to go ahead and read through task 4 and notice that we are asking you to open up Desmos. So if you want to go ahead and get Desmos graphing up, you can go ahead and start pulling your data and see what you can figure out here. Okay, so I'm going to try to lead you through this so that you can kind of double check as we go, that we're using the Desmos correctly. So we're going to insert a table, and then we're going to type our data into the table. So I'm going to go back up to our table so when we're ready, we can pull the data from here. And then, there it is. I needed it to open in another window. There we go. Okay, bear with me here while I get my stuff set up. And then, of course, I have my Desmos over here, so I'm ready to add a table. I'm going to enter these values. I'm going to put 0, and then I can tab into the next cell, and I can keep doing that. 76, 3 and 560, 4 and 512, 5 and 432, 6 and 320. Okay. And then, following these directions here, it says we should be able to see our points graph, and if not, we can adjust our values. So I'm going from 0 to 6 approximately on my X, and I need to go up to like 580-ish on my Y. So let's see, I do want to include, I'll leave that there just to see. And then let's go 600 just to give us that good perspective. Okay, there we go. So now we can see it. Those points are graphed fairly efficiently for us to be able to see that pattern even. All right, so does your graph you drew by hand match the graph on the Desmos? Pretty darn close. Underneath the table type. Okay, so this is where we're going to do this regression, and we're going to make it give us the equation that best matches these data points. Guys, this is actually really relevant right now because essentially, this is what they're doing with the coronavirus data. They're, taking the data and they're inputting it into a program, maybe a little bit more intense than this one, but fairly similar. And they're doing something called a regression, which is going to basically create an equation for you, and then with that equation you can input variables or input data and get output for predictions into the future. So if you have data for 0 days, 1 day, 2 day, 3 day, 4 day, 5 day, 6 day of number of cases, then once you have your regression done, you have a formula you can use. You can plug in, at 20 days, how many cases are we going to have? Input, output. So again, this is extremely important. So I'm glad we're doing this lesson today. Okay, so we're going to do Y1. I'm just typing in what it tells me to type right here. This little squiggle is up above your tab key. And then AX1 squared plus Vx1. The reason why I'm doing these ones is because I'm basically telling it, pull this data. Here's my x1 and my y1, so I want it to pull this data. So that's why I'm putting those subscripts on there, so it knows what x and what y I'm referring to, and that's these up here. Okay, so it created my parabola for me, as you can see, and then it gives me this information down here. So we're not going to get too much into as far as the statistics aspect of it, but it says a curve should appear through all of your points. You should also see some parameters underneath the equation you just typed. Use those parameters to create your quadratic function that models the data. So now we're ready to write in that function that it has given us, this quadratic function. So it looks like our a value is negative 16, so it's negative 16 x squared plus my b is 64 and my c is 512. Okay, so there's my my function that represents height as a variable of time, as a function of time, I should say, because your height is based on time. Okay, this is a progress called regression, and it is used to create equations from a table of data, kind of like what we just talked about. Fortunately, Desmos or a graphing calculator will do all of this math for you, so you can imagine how handy that is compared to doing it by hand. And I've done it by hand, and trust me, it's not fun. So thankfully, we have the graphing calculators that we have access to now. All right, task 5. At this time, I would like for you to go ahead and see if you can get, I'm just scrolling ahead a little bit, see if you can finish up task 5, and then we'll bring it back together to compare answers. Okay, so hopefully you return to question 4 and sketched in the continuous parabola on your graph. And number 14, compare your reasonable domain and range with mine. Make any changes that might be necessary. Number 15, use the function you found in question 12 to verify the height. So essentially when you're using math to verify, you're taking that input output to check it. So I'm checking to see, verify the height when the engine burned out. So essentially I'm plugging in 0 for t because time at 0 seconds is when the engine burned out. So I'm plugging in 0 for t, and I'm checking my output, and my output is 512 feet, which is what we predicted. Number 16, use the graph of the function to approximate the time interval. In other words, you know, what time to what time was the rocket in free fall, and then explain how you determine your answer. So I said that it appears the engine burned out at 0 seconds, but the inertia still propelled the rocket for another 2 seconds, at which time its maximum height was reached, and then it began to free fall. So the rocket was in free fall from 2 seconds until it hit the ground, around 8 seconds. So I'm going to say about 6 seconds total. All right, again, guys, if you need to pause the video at any time to copy this stuff down or to change whatever or modify your answers, please feel free to do so. Looking at the next task here, task 6, we're solving the function at different values. So when we solve a quadratic equation, we are finding x-intercept. So in this context, we would be finding when the Kerbal was on the ground. The x-intercept would be, you know, at 0 height or when it's on the ground. But what if we wanted to know when the rocket reached different heights? So we could adjust that equation to better serve us. So feel free to go ahead and pause the video, and I want you to go ahead and try to get all the way through this task. So stop at 26 for me, please. Okay, so I'll look through this with you. Again, feel free to pause the video at any time to modify your answers or to add to your answers. So number 17, what does the h of t represent? That is the height. That is the y value. It's just like your f of x, which replaces your y value. So in this case, it's the height of the rocket after t seconds. Number 18, what must that equal if I want to know the times that the rocket was on the ground? Well, what's the height when the rocket's on the ground? Of course, that would be 0. So I'd have to let h of t equal 0. So when I moved on to number 19, I actually plugged in that 0 for the h of t, and then I solved my quadratic function by factoring. You could have solved it by completing the square. You could have solved it by quadratic formula. Whatever you were most comfortable with is fine. This one was factorable, so that's what I chose to use, and I got t is 8 and t is -4. So the rocket would be on the ground at 8 seconds and -4 seconds. Okay, so unfortunately, we've almost reached that 15-minute max, so I'm going to have to stop the video and let this be the conclusion of video 1 of 2 videos for this lesson 33.